Okay.
I think that's okay. So we're going to move on to related rates. So if you don't have that handout, just put it up on from the web page. There's a lot of stuff to actually write out on the board.
What does it look like?
I think it's the 2-page handout I gave you.
Yeah.
It says related rates on the top. So I forgot what section this is, but it's 4.1. So this is basically, we're going to use an application of implicit differentiation. But it usually comes in the form of a word problem. So we need to know how to dissect these word problems and talk about them. So related rates talks about, if you know that two quantities are related, so you can have an equation that has two quantities in it, then if you take the derivative of that equation, you now get derivatives in that equation, so it means that automatically the rates of these quantities are related, hence the name related rates. So if I know about the rate of change of one thing, I can talk about the rate of change of something else that I know is related to it by some equation. That's the basic idea. So that's kind of how you know you're doing a related rates problem, is when that's sort of the angle that it comes from. So on an exam, you're faced with a word problem where these two things are kind of present. You know that related rates is something that you want to do, right? So it's a word problem that's telling you about two or more related quantities, which means there's some way these things are related, and you can probably come up with an equation for those things. And the second thing that you're asked to find, you're asked to find the rate of change of something, given that you know the rate of change of something, one of the other things. And so that leads you to a related rates problem. So on one hand, these guys might look scary at the face of it because they're all word problems, but on the other hand, they're easy at the Calc 1 level because you have like a systematic process for doing this, and you will literally always go through this process for any related rates problems that I would give you. Okay, so there's a 6-step process that you can solve any related rates problem that I will give you. So it's just a matter of, one, recognizing that what you're looking at is a related rates problem, and then two, you would go through these steps to actually solve it. And the idea is, of course, you're using derivatives to find the rates of change of something, and to use that to figure out other rates of change. Just to read through the steps, because there's a lot of words here, I don't want to write this down. So the first thing is to read the problem carefully. One, not only do you want to read the problem to figure out it's a related rates problem, because when the final comes around, and even on the third test, there are like 3 situations in which a word problem can come, right? So I'll give you a word problem for exponential growth and decay. You'll have a word problem for related rates. You'll also have a word problem for optimization. So there are a bunch of ways that a word problem can come at you. For marginal functions, those are also word problems. So one thing you want to know is when you're looking at some word problem, how do you know which one of these topics it falls under? And once you know that, what should you do? So related rates, this is how you recognize that it's a related rates problem. Once you recognize that, this is what you do. So the first thing you're going to do is read the problem, make sure you understand that it's a related rate problem. You do want to read it to get kind of the idea. So if there are quantities that are related, you want to know how they're related. Usually, if it's by a geometrical shape, then you have to know how to find the area formula and things like that. So it depends on the situation. But you want to read it to know it's a related rate problem and know how all the quantities involved are related. Step 2 is, it's usually helpful to draw a diagram of the situation, and we'll do that as going through some of these problems here. It's not always necessary, and I'll explain to you how you would know. So for example, if something is described where you can draw a triangle for it, you should draw a triangle and label the parts, and that will help you figure out a relationship to use. Okay, so that's especially if you're not given the relationship, like you're not given an equation. Usually you'd have to sort of draw a situation to sort of figure out an equation that you want to use on your own. So that's the challenge with step 2. Step 3, I think you always want to write down all the information that you currently have in terms of the variables that you did in step 2, as well as what you want to find. Okay, so because these problems can get kind of long depending on the problem, sometimes students get lost and they forgot what they're even looking for in the first place. You don't want to do that, so I would suggest you write down everything you know, write down everything you want to find, and that kind of is your guiding principle. Okay? Step 4, you're going to set up that equation, right? So based on what you did before, based on your picture, you're going to come up with an equation that just relates all the variables in that picture, right? And that you set that up, and that's your step 4. Step 5 is where the calculus comes in. You're going to start to differentiate that equation. You're going to differentiate it implicitly, usually with respect to time, because rate is how things change over time. And then step 6, you're going to plug in your knowns, solve for your unknowns. Right? These are always the 6 steps. Okay, that will solve pretty much any related problem. Well, anyone that I'll ask you, these are definitely the steps you're going to want to use. In general, you will follow the steps in this order. If for some reason you don't need to do a certain step, you skip over that step, but you move on to the very next step, and you continue. Right? So there are times when I might just give you the equation to use, in which case you don't need to draw a picture to figure it out, because I gave you the equation. Okay? So you might skip step 2 in that case, but you immediately move on to step 3 and so on. So you always do these things in this order, right? If something is not necessary, skip over that thing, but make sure you jump to the very next thing. Okay? And that's kind of the idea. At the end of this process, you will be able to answer whatever question was asked to you. So you need to answer the question. And I gave you some tips here as well. So it's very common for some sort of geometrical idea to be used here. And so you will need to remember some of your formulas from geometry, so things about triangles like Pythagoras' theorem. I won't ask you about anything that involves trig, so you don't really need to remember SOHCAHTOA or anything like that. But in terms of like right triangles, you should remember Pythagoras' theorem. In terms of rectangles, you should remember how to find the area of a rectangle, how to find the perimeter of a rectangle, things of that sort. There are also some 3-dimensional things that you'll need, like if you're given something about a cube or a box, you should know how to find the volume of a box, for example, length times width times height, etc. So things like that you will be expected to remember. So just the common kind of shapes. And that being said, I think the best way to get through these problems and learn how to do them is to actually just do them. Learn by doing. So let's actually jump into this. And you're going to see, I might not do all these problems, especially after like, I might do the first 6, but especially after that, it's kind of for extra practice. But the principle should be evident by me going through these first 6. So I'm going to go through these, we're going to follow the steps so you can see how they apply and how you would apply them in each situation. And we're going to end up solving the problem. So let's do example 1 from the handout. Example 1. So it says here, a right circular cylinder undergoes expansion. Its radius is increasing at a rate of 1 meter per second, while its height is increasing at a rate of 2 meters per second. At what rate is its volume changing when the radius is 1 meter in length and the height is 3 meters in length? So notice here, in example 1, you're given rates. It's telling you how fast something is changing, and you're asked to find the rate. That tells you it's a related rates problem. And which means go through the 6 steps. Okay, so that's the important, yeah.
Sorry, do you have an extra? I wasn't here last class.
I don't.
You don't
But
have?
you can pull it up on your phone if you need to.
Okay.
So it's on the website for the class. If you scroll down to the bottom, it says documents. Okay. So I know this word problem, again, if it's on a test, I'm not going to tell you it's related rates. You basically have to figure that out. But notice in this problem here, you're told a rate of increase of two things, and you're asked to find a rate of change of the volume. So because you're given rates and you're asked to find a rate, you know it's a related rates problem. Okay? And so now we would move on to the first step. So the first step was read carefully. So now I read it, I realize it's a related rates problems, and I realize it's talking about a cylinder. So then that kind of piques my brain to think about all the things I know about cylinders. So 2, diagram, I mean, it's not super useful here, but let's go through it anyway. So basically a right circular cylinder is just a cylinder where the cross section is a circle. And it's mentioned the radius, right? So the radius is going to be this part here. And it also mentions the height of the cylinder, which is here. Okay, so that's your diagram. 3. Let's write down our knowns. What do we know and what do we want? Right, so that's going to be the third step, to sort of figure out what do I know about this object that you just described to me. Well, I know about the rate of change of the radius, right? So that's just a derivative with respect to t, so I know dr dt. Right, that's the rate of change of r with respect to time. And what is that? It's 1 meter per second. I'm not going to be crazy with the units here, whether you write units in your answers or not. I'm not going to care particularly too much. But in a physics class, that would be super important. I don't really care about the units here. But it's 1 meter per second. And what do we know about the height? It's increasing at 2 meters per second. Now, one thing I want you to realize is that because these are, the sign of these answers are going to mean something, right? So, because it's increasing, they're both increasing, right? So here you have to remember in a derivative that increasing means the derivative is positive, okay? Which means if the question said one of these were decreasing, you'd have to put a negative sign. And that's why step 1 is very important. You need to read to figure out how you're going to set these things up. So we know these two rates. I know these are positive numbers because they're increasing and the values are given here. Okay. Now what do we want to find? At what rate is the volume changing? So what kind of thing is that? What rate are we asked to find? dV dt. So what you want is dV dt. And I'm even telling you when I want it. When the radius is 1 and the height is 3. So now we've done the first 3 steps. We read the problem, understand that it's related rates, understand how things are working together. We understand that things are increasing, therefore the rates are positive. 2, we went through draw a diagram. Hopefully that will spark some memories, fond or otherwise, about high school geometry class that will help you come up with some formulas for this. 3, we write down what we know and what we want to find. So we know at the end of the day, I need to find dV dt. I need that answer. I need a value for this answer under these conditions. Okay. So the next thing, which hopefully step 2 will help you with, is you want to come up with an equation that relates all these variables. Right? So one thing you'll notice, what are the variables here? There's an R, there's an H, and there's a V. So I need an equation that has all those guys in it. So you guys remember how to find the volume of a cylinder?
pi r squared times height.
Pi r squared h. Right? Anything that is like this, where it's the same shape throughout the object, right? You pretty much have a circle and you're elongating it. It's the area of the base times the height. This is something that's called a prism. So we take the area of a circle, which is pi r squared, multiplied by the height, and that's the volume. So here I came up with an equation that relates all the variables in this problem. Okay. So that is step 4. Okay. And step 4, you kind of use step 2, or basically whatever the problem describes, to come up with that equation. So now we move on to step 5. I'll see if we remember how to differentiate. It's been a little over a week. let's see how much differentiation we remember. So 5, we're going to differentiate implicitly with respect to time. I mean, time is my independent variable, so if I differentiate anything that doesn't have a t in it, I have to multiply by the derivative because of the chain. Okay. So, how do I differentiate this? What's the derivative of v with respect to t? dv dt. How do I differentiate this? 2 pi r dr dt, right? Because my r is not t, right? So my r is a function of t, so there's some inside function there. So I have to multiply by dr dt. Right, that's implicit differentiation happening here. So that word implicit is important, right? Plus dh dt. Okay, so now I want you guys to realize what happened here. I did the product rule, right? Because there were two functions, so I did the product rule. Pi is a constant, so I kind of just leave it alone, right? So I have to differentiate this, leave that alone, plus differentiate this, leave that alone. The difference is the differentiation is implicit, meaning r and h are not our input variables. T is the input variable. So whenever I differentiate an r function, I have to multiply by r prime. If I differentiate an h function, I have to multiply by h prime, because that's the chain. Okay? So that's going to be the derivative. Which leads us to step 6. Now we can actually solve the problem. I'm going to plug in the knowns and solve for the unknown. The guy we want is dv dt, but we know all of these guys, right? We know what r is. They told us r is supposed to be 1. We also know what h is. H is supposed to be 3. dr dt, we also know what that is. I wrote it down over here. I wrote those down over here. So that was also supposed to be 1. And dh dt is supposed to be 2. So because I know all the values here, I can just plug them in at this point. Plug in knowns. Solve for unknowns. So here I have dv dt, that's an unknown. In fact, that's the guy I want to find. And I'm going to plug these guys in. So this is pi times r, which is 1, times h, 3 times dr dt,
1.
plus pi times 1 squared. dh dt was 2. So this becomes what? 6 pi plus 2 pi. The answer is 8 pi. So the volume will be changing by, I forgot what the unit of time. It's per second. So it's meter cubed per second. But like I said, I don't care if you write the units. No, it's not physics class. It's not super important. I care that you can get the right values. As long as all your units like match up, I'm not going to make them not match up. But that's basically the idea. Right? So by knowing about the rates of change of my radius and my height, I can talk about the rate of change of my volume, which is a related quantity. Right? It's related by this equation. Any questions? Yeah, so like I said, you're always going to go through these 6 steps. It's not going to... So the only parts, well, we've erased it now, but the parts that are going to be really different conceptually are going to be like the equation that you come up with and step 2, right? So that's where you kind of have to figure things out, but the rest of it is kind of like following your nose kind of thing, right? So you need to figure out a picture that sort of describes the situation so you can figure out what's going on and then come up with an equation. But once you get through those 2 hurdles, the rest of it is straightforward. You're just going to differentiate and plug in what you know and what you want and solve for what you don't know. One possible issue, and we'll have examples that deal with this issue, is that it is possible that after going through this one time you get to step 6 and you have more than 1 unknowns, which that's a problem. But you can deal with that easily. All you have to do is if you get to this point and there's something that you don't know, usually what can happen is you can go back to step 4 in the original equation, solve for that thing you don't know, and then come back and put it in, right? So that's the only other hiccup that can potentially happen. But otherwise, it's a straightforward, streamlined process. Any other questions? Yeah.
So I still don't quite understand what the dr over dt is and dh over dt is. Why to multiply it in the product?
Oh, well, so this is kind of going back to implicit differentiation. Remember if you had something like x squared y equals 5, x squared y cubed equals 5 or something similar. Now when we're differentiating this, how did we actually do it, right? We realized that these were 2 functions, but my y was a function of x, right? So if I differentiate this using the product rule, I differentiate the x, I leave the y cubed, plus I leave the x squared, and I differentiate the y cubed, right? But because this y is like a function, I had to multiply by the derivative of the inside, and multiply by y prime, right? So that's the same idea. If I differentiated the r, I multiplied by r prime. And if I differentiate the h, I have to multiply by h prime. Because they're both like functions of another variable. So it's like the chain rule. So it's like if I had something cubed and I wanted to differentiate that, then I differentiate the outside, multiply by a derivative of the inside. That's a chain rule. So it means that whenever I'm differentiating a certain variable, I have to multiply by its derivative because of the chain rule. What we're doing here is implicit differentiation. That's one of the topics that we covered a little bit before the break. So as long as what you're differentiating is not a t, the thing is we never had to put x prime here because x was our input variable. And technically you could put x prime, but that's just 1, so it didn't matter. But here you're going to have to always put the derivatives because these variables are not the original. T is always going to be your input variable for related rates. So anything that's not a t, you have to multiply by the derivative when taking the derivative because it's the chain rule. Let's go through example 2. So the length of a rectangle is increasing at a rate of 8 centimeters per second. Its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? So again, I read that. The takeaway should first be, it mentioned rates, right? So rates were given to you. I was told the rate of change of the length and the width, and I was asked for a rate. It asked me about the rate of change of area, so I know it's a related rates problem. Once I recognize that as a related rates problem, I go through these 6 steps. Okay. So step 1 is to read the problem carefully so we recognize it's related rates, and we kind of have the situation in mind. It's going to be 1 describing a rectangle. So step 2, here I'm going to throw in that diagram. What's the diagram? Rectangle. Alright, so I'm going to draw a diagram. I'm going to label the diagram. So what do we want to call this length and width? L and W? You can call it whatever now. So let's call this W. Let's call that L. Right, so there's my diagram. I know that my length and width are changing, so that's sort of the picture. So that's kind of the picture I have in my head. Move on to 3. Write down what we know. What do we want? Put some space here. So what are the rates that we know?
Is 8 centimeters.
So how can I write that down? dl dt is
8 centimeters.
8, and it's positive 8 because it's increasing. We also know dw dt. dw dt is what?
3 centimeters per second.
3. Okay, what do we want to find?
Area.
dA dt. How fast is the area changing when, under what conditions?
When length is 20.
When L is 20
Width is 10.
and W is 10. So that's step 3. So now we know what we have and where we need to get. Okay, let's move on to step 4. What is step 4? I need to figure out an equation that relates all these variables. So I have variables L, W, and A. These are all the variables under consideration. Can you come up with an equation that relates all of these?
2L.
Come again? Right, area equals length times width. Right? So there's an equation that relates all the variables that I mentioned in step 2 and step 3. Step 5. Now we're going to differentiate. And remember, you're differentiating implicitly. T is our input variable here. So what's the root of A? dA/dt. The root of that.
L times dw/dt.
So I differentiate the W plus,
W times dl/dt.
now I differentiate the L. So I did the product rule with the implicit differentiation. So these guys are two functions. So I have to differentiate one, leave the other, plus differentiate this one, leave the first one. Which now leads us to step 6, and I think we know all of those guys, so.
The marketplace?
Step 6 is basically to plug in. So dA/dt, I don't know that. That's in fact what I want to find, so let's leave that here. L
20.
is 20 dw/dt,
3
3
plus
dl/dt,
8 times 10.
and W
10.
is 10. So that's what, 60 plus 80, which is 140. And technically this is centimeters squared per second, but as I said, 140 is fine. Units can be very beneficial, but mostly in like physics class, because you can always check your answers using units, but here we won't care too much. Are we sort of getting the idea? Move on to another example. Okay, so we're on to example 3. A 15-foot ladder is resting against a vertical wall. The ladder begins to slide away from the wall at a rate of 2 feet per second. What? Oh, was it, what was it? Was it like Batman or something?
Yeah.
Yeah. So anyway, the foot of the ladder is sliding away from the wall at 2 feet per second. At what rate is the top of the ladder sliding down from the wall when the foot of the ladder is 9 feet from the wall? So step 1, I read the problem. I recognize it as a related rates problem because I'm given rates and I'm asked to find the rate. Step 2, what does our diagram look like in this case? It's going to be a triangle. Why? Because if you draw a vertical line to represent the wall, you know a ladder is leaning against the wall. So that's your ladder. And this is, of course, the ground. So basically, we end up with our diagram here is kind of like a right triangle. And now I'm going to sort of throw in variables here. So what distance you want to be the foot of the ladder away from the wall? Well, it's kind of like reminds me of the xy plane. So I'm going to call this x just for. So I don't think I gave you any. I didn't give you any variables, so in theory you can call them whatever you want. So let's call that x and call this height y. And what is the hypotenuse of the triangle? It's 15. Right? Now this is written on the handout, but I'll mention it now. Right. Label anything not changing by a constant. Right, so the length of the ladder is not changing. Make sure you label that with a constant. Why? Because if you put a variable there, then you're going to do implicit differentiation. You have to multiply by the prime. But the thing is, the prime is going to be 0, but students often forget to plug in 0. And so they have all these extra variables and these terms that they don't know what to deal with. It's much less confusing to just, from the beginning, anything that's not changing, label it by whatever its value is. So the value of the ladder is 15. It's always going to be 15, so you label that 15. What is changing is that the foot of the ladder is sliding away, so this distance here is moving, right? You also know that this distance here, as the foot of the ladder slides that way, this guy is going to slide down. So these two are changing, and that's why I label them by variables. The ladder itself is not changing, therefore I label it with a constant. Okay? Now, I know that my x is increasing because it's sliding away from the wall. Okay, but that's basically my diagram. That's sort of a pictorial representation of the situation that's going to help me with setting up that equation. Let's talk about step 3. What do we know? What do we want to find?
The dx dt is 2 feet per second.
Do we know anything else? That's pretty much the only rate we're given. Okay, what do we want? It says, find the rate at which the top of the ladder is sliding down the wall. Right? So that's talking about how fast is this motion moving, but that length is described by y. So what we actually want is dy dt. When
X equals 9.
When x equals 9?
Yep.
X equals 9. So I read the problem to understand the situation. It's a related rates problem. I also, by reading the problem, I can come up with this picture. After coming up with this picture and seeing and labeling with variables, I can describe what I know and what I want to find in terms of these variables. Right? So I know this rate. I want to find this rate at that point. Which leads us to step 4. So step 4 is to come up with an equation. So what's the equation here? Huh?
Do we use a squared plus b squared plus c squared?
Pythagoras' theorem. Okay, so what would the equation be by Pythagoras' theorem for this right triangle?
X squared plus y squared equals 15 squared.
So that's my relationship. Step 5. I'm now going to differentiate this equation implicitly with respect to time. So I'm going to go through one term at a time and differentiate. Derivative of x squared, 2x times dx dt. Now the difference is here, t is our input variable. So don't mix this up with what we were doing before. When we differentiate x, we didn't have to do anything. In this case, we have to do something because x is not the input here. T is always the input. And so when I differentiate by x, I need to multiply by x prime. And so I have that. Plus this guy, very similar, is going to be 2y times dy dt. Derivative of 15 squared?
0.
0, because it's a constant. Now if you had plugged in a value for this like z, you'd have 2zd, zdt, and then you'll worry about what's z and what's dz dt, and then you freak out and you do something. It's much easier to just label out a constant from the beginning so you know I don't have to worry about it. Okay, it's just a 0. And so now what? Right, exactly. We're always following the same steps. That's the basic thing I want you to get through your heads with these problems, right? So related rates and optimization, there are some of the bigger problems that you'll see on a final, but they're easy in the sense that there's always one process to get through any of them. Okay? So you'll always know what to do next, provided you actually know the steps are. So it's important that you remember what I wrote in the box here. So again, I'd recommend that you go through this handout and read it in detail again, but eventually you'll remember all the details. You just need to remember like the things in bold, like the real things that pegs your memory as to what you need to do. Okay, so we need to plug in. So what do we have here?
We have x, d of x.
We have x. We know this.
We can solve for
We want to find this. Do we know why?
No. Well, we can solve for that.
Okay, so here we're in a situation where we have more unknowns. We have more than one unknowns. That's kind of an issue, but the idea is here, why? We need to know why. No, why as in the variable. We need to know what y is. So if you get to step 6 and you want to be plugging everything in, but you don't know everything, what you do is you go back to step 4. Right? So anything that you need to find, you can go back to the original equation, because this is the equation that governs all your variables. If you want to know what the variables are doing, this is the guy that tells you. And so we'll go back to step 4, and we know that x squared plus y squared is equal to 15 squared. So when we know our x value, what was that, 9?
9.
When x equals 9, this means that 9 squared plus y squared is equal to 15 squared. This means that y is equal to?
12.
Y is equal to 12. Now how do you find that 12?
When you do 9 squared, you get 81. 15 squared is 225. So when you subtract 81 on both sides, you get y squared equals 144, and then you do the square root of it as well. So just by that.
Yeah, you can do it that way. There's another way. Anyone notice a trick here that we can use?
It's like one of those, like, it's hard to try to
It's one of the special triangles that are involved here, right? So it's like called a 3, 4, 5 triangle. So if you have a right triangle, you know that one side is 3 and the other side is 4, then this side must be 5. And if that side is 3 and that side is 4, and that side must be 5. So if you have a triangle where you know, for example, the hypotenuse on one other side, you can figure out the other side easily, right? Because these numbers, they're called Pythagorean triples. They always come together. And the nice thing about these triangles is they work proportionately. So if I were to multiply, for example, each side by 3, the relationship holds. So what you notice is that this side is 9, that side is 15, so it forces this side to be 12. So you could actually know that without going through the calculations, but if not, yeah. So however you do it, from solving this equation for y, you'll get y equals 12. So things like a 3, 4, 5 triangle is sometimes a shortcut. You can see the answer right away without going through all the calculations. And so now we can actually finish step 6. What is, so we have this equation. Let's start plugging things in. What's, the x value is 9. dx dt was what? 2. The y is now 12, which I found by going back to step 4. dy dt, I don't know, I want to solve for dy dt. So now I solve for that. I can divide both sides by 2. And so this would mean that my dy dt is equal to, move this to the other side, that's minus 2 times 9 divided by 12. I can say 2 into 12 goes 6 times, 3 into 6 goes 2 times, and 2. So this is minus 3 over 2. And this is in feet per second. Like I said, I don't really care about the units, but it's feet per second. Now, one important thing here is notice that we got a negative sign. Does that actually make sense?
No, because of direction.
Yeah.
Because it's going down.
Right, so the thing is here, if this is x and that's y, if x increases, you should realize that what's going to happen is y is decreasing. Right? So your answer should be negative, which means at the end of the day with these problems, you also need to kind of know whether your answer makes sense or not. So you will take the interpretation of the derivative that a positive number means it's an increasing or getting larger, while a negative number means it's decreasing or getting smaller. And in this case, a negative answer actually makes sense because we do expect the y value to be decreasing. So if you didn't get a negative answer here, it means you made a computational error somewhere, you need to find it, or maybe your equation was slightly off, right? But at the end of the day, when you do get to the final answer, you should kind of have an idea, especially from looking at the picture, whether you should be getting a positive number or a negative number, or maybe even slightly how large it should be, right? So if one of these guys is just changing by 2, but you get this answer is like 1,000,000, that's obviously going to be too big because a quadratic doesn't grow that fast. Like there are a lot of those little things that you can worry about. But we'll stop right there. We'll do some more examples next time. Yeah, like I said, some of these you can do them on your own for extra practice. I can help you on the test. But I want to get through the next, at least the next 3 we can do, and then we'll move on. As far as the test, I have the suspicion after talking to the next class it will be Friday, but at the end of the day today I'll let you know for sure if it's next week Tuesday or next week Friday.